Before we begin, take a moment to get comfortable. Let your arms go heavy, your breath slow. And as you listen, feel free to leave a comment sharing what time it is, where you are, and what city or village you're listening from. It's love to know. And if you'd like more quiet stories like this one, don't forget to subscribe so they gently appear when you need them most. Now, let's begin. Tonight, we begin not with motion, but with stillness. A kind of cosmic pause before the concept of movement had even emerged, before stars, before atoms, before even time itself, as we now understand it. A universe, perfectly quiet, and then dash energy. But the question we arrive at, softly and carefully, is this: why does light move at a fixed speed, not faster, not slower? And how does the entire structure of our universe depend on that limit? To understand this, we must begin with the fabric of space and time. The cosmos, in its rawest form, is not made of matter or light. It is made of space-time for dimensions, blended into a single, flexible entity. 3 dimensions of space, 1 of time, bound together by geometry, motion, and gravity. And within this fabric, there are rules, not invented, not decided. We discovered it quietly, patiently, through observation. Light, as we call it, is not just illumination. It is an electromagnetic wave, a ripple in electric and magnetic fields. And those fields propagate, not instantaneously, but at a finite speed, roughly 299,792,458 meters per second in a vacuum. A number so constant, so unshakable, that modern physics builds itself around it. But why? The origin of this number is not mechanical. It is not determined by gears or celestial levers. It emerges from the very structure of Maxwell's equations. In the 19th century, James Clerk Maxwell unified the laws of electricity and magnetism. He found that changing electric fields produce magnetic fields, and changing magnetic fields produce electric fields. Together, they form self-sustaining waves rippling outward through space. And when Maxwell derived the speed at which these waves should move, it matched the measured speed of light exactly. This was no coincidence. Light was not a separate entity. It was an electromagnetic wave, a natural vibration of the fields that fill all of space. And its speed was determined by 2 constants: the electric permittivity of space and the magnetic permeability of space. 2 numbers, both small, both universal, and when you take their inverse square root, get the speed of light. Exactly. This speed, 299,792,458 meters per second, is not just a property of light. It is a property of the universe. It's the maximum speed at which cause and effect can travel. No information, no influence, no push, pull, or interaction can go faster. But why should this be? To explore that, we turn to Einstein. In 1905, Albert Einstein published his theory of special relativity. It began with 2 principles. First, that the laws of physics are the same for all observers in uniform motion. Second, that the speed of light in a vacuum is the same for all observers regardless of their motion or the source's motion. These ideas seem simple, but their consequences are profound. If light always travels at the same speed for everyone, regardless of motion, then time must bend, length must contract, mass must increase, satiety must disappear. This is not metaphor. It is measurable, repeatable, fundamental. In relativity, the speed of light is not just a speed. It is a boundary, a horizon, a limit written into the equations of space and time. Imagine a spaceship. It accelerates gradually toward the speed of light. As it does, the energy required to go faster increases, not linearly, but asymptotically. To reach the speed of light, would require infinite energy, a concept with no physical meaning. A boundary the universe will not cross, because as you go faster, time slows, distances shrink, and from the perspective of the traveler, reality reshapes itself. No matter how fast you go, light always outruns you. It never recedes, it never slows, it simply remains constant, quiet, unwavering, and yet light itself is timeless. From its own perspective, a photon experiences no time at all. It is emitted, it is absorbed, but in its own frame of reference. It exists only in those two events. No passage of time, no distance crossed, and this is where the boundary becomes even stranger, because light does not simply move at the speed limit. It defines it. It lives on the edge of causality, on the border between what can influence and what cannot. When we say something travels at light speed, we are saying it experiences no time. It does not age. It does not wait, and nothing with mass, no particle, no object can reach that state. This is not a flaw. This is not a technological limitation. It is a structural truth. Light speed is not a maximum in the way a car's speed limit is enforced. It is a maximum in a way a square cannot have 5 sides. This is written into geometry, and yet this limit allows the universe to make sense. If signals could travel faster than light, causality would break. Effects could precede causes. Paradoxes would emerge, and the logical flow of time from past to future would unravel. The light speed limit preserves consistency. It defines the edge of each observer's experience. Each event in spacetime has a light cone, a boundary of influence. Everything inside the cone can be affected. Everything outside cannot. This cone grows outward at the speed of light, defines what we can see, what we can touch, what we can ever know. It is the horizon of knowability, and it is everywhere, even the most distant stars. Their light reaching us after billions of years. Respect this limit. Some galaxies, so far away, move from us faster than light due to the expansion of space itself. But even then, their light cannot reach us. They slip beyond our causal horizon. The universe, in its grand stillness, respects the limit, because without it, there would be no time, no memory, no sequence, no life, and so the speed of light is not a speed. It is a structure, a wall, a law, not enforced, but built in. The next time we look at the stars, or the glow of a candle, we're not just seeing light. We are seeing the edge of possibility, the fastest anything can move, the rhythm of cause and effect, the heartbeat of the cosmos. There is a quiet elegance to the structure of the universe, and at the heart of that structure, invisibly woven through the cosmos, K, is the constant speed of light. It is not just a measurement, K. It is a universal boundary that connects mathematics, physics, and reality in ways both profound and practical. As we continue exploring why light has a speed limit, we must now look deeper into the consequences of this speed. Let us shift softly from theory to nature, to what the speed of light means for the stars, the planets, and even for life. Light is not the only thing affected by the cosmic speed limit. Gravitational influences cannot travel faster than light either. This is one of the quiet consequences of general relativity. If the sun were to vanish suddenly, a purely hypothetical scenario, of course, Earth would not notice right away. The gravitational pull of the sun would continue to hold Earth in its orbit for 8 more minutes, just as its light would continue to shine down for 8 more minutes. Gravity, like light, is limited by this universal speed, because gravity is not a force that acts instantaneously across space. It is a curvature of space-time and changes. In that curvature, propagate outward like waves. These waves are known as gravitational waves. They ripple through the fabric of space-time when massive objects accelerate like black holes colliding, or neutron stars spiraling inward, and we have detected them. In 2015, the LIGO Observatory recorded the first direct observation of gravitational waves. Two black holes had merged over 1 billion years ago, and the echo of their union reached Earth at the speed of light. The detectors moved by less than the width of a proton, but the signal was clear, and it confirmed what Einstein had predicted a century earlier. The speed of light is not just for photons. It is the speed of all massless interactions, including gravity. This limit unites all the forces of nature. Even particles, the carriers of fundamental forces, obey this rule. Gluons, which bind quarks inside protons and neutrons, W and Z bosons, which govern radioactive decay, and photons, which mediate electromagnetic interactions, all move at this same invariant speed when in a vacuum, if they are massless. This is why the limit exists in the first place. Massless particles have no internal clock. They do not age. They do not slow. They move along what physicists call no geodesics, paths that are neither inside nor outside the light cone. Precisely on its surface, they define causality's boundary. But perhaps the most quiet and overlooked aspect is the role this limit plays in making space and time interchangeable. In Einstein's relativity, time is not separate from space. They are fused into space-time, and the only thing that connects them cleanly is the speed of light. Why? 'Cause in the mathematics of space-time, distances and durations are measured using units that need to be compatible. You cannot add apples and oranges unless you find a conversion factor. The speed of light is that factor. It converts meters into seconds. It tells us how far light travels in one tick of a clock, and in doing so, creates a system where time behaves like a dimension, just like space. In some equations, physicists even set the speed of light to 1, not because it is numerically trivial, but because it simplifies the language of the universe. In these natural units, space and time become mirrors of each other. This is not a trick. It is not a shorthand. It is a reflection of how reality behaves. The constancy of light speed makes the laws of physics symmetric. Quantities, invariance, the idea that physical laws are the same regardless of orientation or velocity. If light had no limit, or if it varied between observers, then the entire framework of physics would shatter. Electricity, magnetism, gravity, thermodynamics, all would become inconsistent. But with this one rule, the cosmos becomes harmonious, and yet the speed of light is not always observed as 299,792,458 meters per second. This may sound like a contradiction, but it is not, because when light passes through a medium like glass, water, or air, it slows down, not in the fundamental sense, but in the observed sense. Light in a vacuum always travels at its full speed, but in matter, it interacts with particles. It is absorbed and re-emitted. It is scattered. Its wavefronts are delayed. This makes it seem slower, but between those interactions, it always moves at full speed. The index of refraction quantifies this slowdown. It tells us how much light bends or refracts when it enters a new medium, in diamond. For instance, light moves more than 2 times slower than in vacuum. This is what gives diamonds their sparkle. It is also why lenses work, why rainbows form, and why fiber optics can bend light around corners. But in a vacuum, when no matter interferes, light always moves at the limit, the perfect speed, the constant that binds the universe. And now we must visit a subtler question. What if the speed of light weren't what it is? What if it were faster or slower? Physicists have pondered this, not as a speculative fantasy, but as a means to understand how finely tuned our universe is. if the speed of light were significantly slower, for instance, then relativity's effects would become visible at everyday speeds. Time dilation, length contraction, they would dominate human life. GPS would not work. Satellites would drift. Even walking across a room would involve relativistic calculations. On the other hand, if light were much faster, then these effects would become imperceptibly small. The universe would behave more like Newton imagined, but only on the surface, because a faster light speed would alter the strengths of the fundamental forces. It would change how atoms bond, how stars burn, how life emerges. Nuclear reactions in stars depend on delicate balances. Too fast and fusion cannot occur. Too slow and stars collapse. The very chemistry of life depends on light's limit. Even the size of atoms is governed by the speed of light. The Bohr radius, a key atomic measurement, includes the speed of light in its formula. If that speed changed, atoms would shrink or swell. Molecules would break. Biology would dissolve. So the light speed limit is not arbitrary. It is not just a cosmic curiosity. It is the silent scaffold holding reality together. Not just physics, but chemistry, thermodynamics, biology, cognition, because neurons fire based on electrical signals, and those signals depend on the flow of charged particles, and those particles obey the laws of electromagnetism, which rely, ultimately, on the speed of light. Our thoughts, our memories, our perception of time are rooted in this limit. We are made of processes, and those processes are governed by signals, and all signals must obey the cosmic speed limit. Even in dreams, light outruns us. It always has, it always will, always will. To understand why light has a speed limit, one must also consider the nature of space-time itself. Space-time is not merely a backdrop or a container for the universe. It is not like a cosmic stage on which particles and forces act. It is an active participant in the structure of reality. It bends, it warps, it reacts. Mass tells space-time how to curve, and curved space-time tells mass how to move. This relationship, outlined by Albert Einstein in his general theory of relativity, is one of the most quietly profound truths in all of physics, and the speed of light is woven through every layer of this truth in Einstein's equations. The speed of light appears as a constant that unifies space and time. Without it, there would be no metric to describe how far an object moves, not just in space, but in time. Distance and duration would become meaningless. Causality would fade out, and so space-time itself is built with the speed of light as one of its foundational parameters. If you imagine space-time as a smooth surface, like a soft rubber sheet, then the speed of light is the slope limit. No signal can move across the sheet faster than this limit allows. You can pull, stretch, or compress the sheet, but nothing can ripple across it faster than light. Even black holes, the darkest and most extreme objects in the cosmos, respect this limit. Nothing can escape a black hole's event horizon, because K at that boundary. Even light cannot travel outward fast enough to overcome the inward pull of SPACMAP. It is not that light is too weak. It is that space-time itself has become so distorted that all paths, even those pointing away, curve back inward. The escape velocity at the event horizon equals the speed of light. No signal, no matter, no information can exceed it. This makes black holes not only fascinating, but fundamentally quiet. They absorb, they contain, they do not let messages out, and this is consistent with causality, the principle that effects cannot precede causes. If information could travel faster than light, it could arrive before it was sent. This is not just paradoxical, it is physically incoherent. A signal arriving before it is sent would allow time travel into the past. It would unravel the fabric of events. Cause and effect would dissolve. The speed of light is not just a speed. It's a firewall protecting the logical structure of the universe. Some physicists have even referred to the light cone, the geometric shape that defines the boundary of causal influence, as nature's way of enforcing order. Inside the cone, events can influence each other. Outside the cone, they are forever disconnected. And the slope of that cone, it is the speed of light. If we were to chart every event in space-time, every heartbeat, every supernova, every movement of every atom, then each one would sit inside its own light cone. Its influence would radiate outward at light speed. Nothing faster, nothing beyond. This is why all physical theories, from classical mechanics to quantum field theory, obey the same fundamental constraint. Now, in the world of quantum mechanics, things become less intuitive. Particles appear to behave as both waves and particles. They can become entangled, sharing a strange connection that seems to link them instantly across space. Einstein famously called this spooky action at a distance, because when two particles are entangled, a measurement on one seems to instantly affect the other, even if they are far apart. But this does not violate the speed of light. No information is transmitted faster than light. The measurement outcomes are random, and only when both measurements are compared through slower than light communication do the correlations become apparent. Entanglement is strange, but it respects the speed limit. The universe, even at its most mysterious, follows its own quiet rules, and light itself, in all its manifestations, obeys them. Whether it is a beam from a distant star traveling for billions of years to reach a telescope on Earth, or a photon emitted in a lab experiment, it never disobeys the limit, even in curved space-time, even in expanding space. This brings us to another subtle aspect of cosmology, the expansion of the universe. Galaxies appear to be receding from us, not because they are moving through space, but because space itself is expanding, and some galaxies, very far away, appear to be receding faster than the speed of light. Is this a violation? No, because the speed limit applies to motion through space, not to the expansion of space. Space itself can stretch, and when it stretches, it carries galaxies apart. This is why the observable universe has a horizon. Beyond a certain distance, about 46 billion light years, galaxies recede faster than light due to space expansion, and their light will never reach us. They are not breaking the rules. They are following a different set of rules, those of general relativity and cosmic inflation. Even so, local physics remains intact. Nothing can outrun light through space. No spaceship, no signal, no force. This is why science fiction depictions of faster-than-light travel, warp drives, wormholes, hyperspace often require exotic matter, negative energy, or other speculative elements, because to move faster than light is not just to move quickly, it is to move outside the fabric of known physics. Now, let us turn to something even quieter: the implications of light speed for time itself. Time, in relativity, is not absolute. It flows differently for observers in motion. A person traveling near light speed would experience time more slowly than someone at rest. This is not a trick of perception. It is measurable. It is built into the equations. Astronauts aboard the International Space Station age very slightly more slowly than people on Earth. Not enough to notice, but enough to detect with atomic clocks. This is time dilation, a consequence of the constancy of light speed. If light had no limit, there would be no time dilation, no relativistic mass, no contraction of length, and our GPS satellites, which rely on precise timekeeping, would fail even more quietly. The speed of light underpins the concept of proper time. The time experienced by a single observer moving along a path in spectrometry. This proper time differs between observers. Because different paths through space-time, different velocities, different gravitational influences yield different experiences of time, but all are bound by the same light speed structure. No observer can move from one point to another faster than a light beam could. The geometry of space-time enforces this. It is why we never see signals from the future, why we do not receive messages from stars that no longer exist, why time, for all its mystery, only flows forward at a pace determined by our motion, our gravity, and the ever-present speed of light. The speed of light is not just the fastest speed in the universe. It is the most reliable, the most universal, the most deeply woven constant in all the fabric of physical law. It is the same in every direction, no matter where it is measured, and no matter how fast the observer is moving. This principle, the invariance of the speed of light, is not merely observed. It is enshrined. It forms the bedrock of special relativity. In the early 20th century, scientists tried to measure differences in the speed of light depending on Earth's motion through space. They found none. The famous Michelson-Morley experiment, quiet, precise, and subtle, detected no variation, no ether wind, no directional bias, just the same speed. Always. This puzzled many at first, but it led Einstein to propose something radically simple. The laws of physics, including the speed of light, are the same in all inertial frames. This idea overturned centuries of thinking because it meant that space and time themselves must adjust depending on motion, not light, not the signal, but the stage. So time contracts, distances stretch, mass increases, all to preserve the speed of light. This constancy is not a limitation imposed on light. It is the result of how reality is structured. It is baked into the geometry of the universe. Imagine two observers. One is standing still. The other moves past in a smooth, steady motion. Each holds a flashlight. Each sees their own light beam travel at 299,792,458 meters per second. But each also sees the other's clock ticking more slowly, and their rulers appearing shorter in the direction of motion. Both are correct, because time and space flex in response to motion, all to preserve the speed of light. Even when a light source moves, whether toward you or away, the light speed does not change. Only its wavelength does. This is the Doppler effect. It's why light from stars moving away appears red-shifted, and light from stars moving toward us appears blue-shifted. But the speed remains untouched. This is different from sound. Sound travels through a medium, air, water, or steel. Speed depends on that medium. To move the source or the observer, and the speed of sound changes. But light needs no medium. It is self-contained. It is an electromagnetic wave, a ripple in electric and magnetic fields, traveling in lockstep, each field creating the other, self-sustaining through space. And because of this nature, it does not slow or accelerate based on who's watching. It simply is. The equations that govern light. Maxwell's equations describe how electric and magnetic fields propagate. When solved, they yield a wave traveling at one precise speed. That speed is derived from two fundamental constants: the electric permittivity of free space epsilon EB, the magnetic permeability of free space mu EB when combined. These yield C equals 1 square root epsilon EB mu Eve. This is not a number chosen by nature at random. It is a ratio determined by how space responds to electric and magnetic fields. This makes the speed of light not a property of light itself, but a property of space. Wherever space exists, these constants apply, okay? And so the speed of light applies it, is a universal property, like the boiling point of water under standard pressure. or the freezing point of pure hydrogen. Except this is deeper, more global, more absolute, because it applies across the entire cosmos, across galaxies, nebulae, voids, and clusters, across all of space. If an alien civilization a billion light years away measured the speed of light, they would get the same number. Their equations would match ours. Their limits would mirror ours. This is why the speed of light is often used as a measuring stick in cosmology. Distances are not just in kilometers, they are in light years. Time is not just in seconds, it is in light travel time. When we say a galaxy is 10 billion light years away, we mean the light from it has taken 10 billion years to reach us. We are looking back in time. The farther we look, the older the light. And because light moves at a fixed pace, the universe becomes a time machine. Telescopes are not just windows, they are archives. They reveal not how things are, but how they were. Because light takes time now. Imagine what would happen if this speed were different. What if light moved faster? Communication would be quicker. Society would stretch farther. The structure of atoms, which depends on light speed electron behavior, would change. Chemistry would be different. Stars would burn at different rates. Fusion would proceed along unfamiliar lines. Planets might not form. Life as we understand it might be impossible. And if light moved more slowly, relativity effects would intensify. Time dilation would occur at lower speeds. Black holes would form more easily. Light would take longer to cross a room. The entire scale of the universe would shrink. And again, life as we know it might not exist. So the speed of light is not just a cap. It is a balance point, a fine-tuned feature of the universe. It allows for causality. It allows for atoms. It allows for energy transfer, radiation, communication, vision, and memory. Every photon that has ever touched your skin, every spark that has passed through a wire, every distant star whose shimmer has reached your eye, has traveled at the same constant speed, unchanging, patient, faithful to its limit. And so we rely on it. We build technologies around it. Fiber optics, GPS, lasers, quantum clocks. We define units of distance based on it. The meter, originally defined as a fraction of Earth's circumference, is now defined in terms of how far light travels in a fraction of a second. Light speed defines length. Light speed defines time. It even defines mass through Einstein's famous equation, E equals mc. The energy of an object is proportional to its mass multiplied by the square of the speed of light. This equation is not merely symbolic. It tells us that a small amount of mass can be converted into an enormous amount of energy because c squared is a huge number. This is why nuclear reactions release so much energy. A tiny mass difference becomes a flood of energy because light's speed squared is 89 quadrillion, 875 trillion, 517 billion, 873,681,764. Nearly 90 quadrillion in meters squared per second squared. Again, speed of light is not passive, it is active. It tells us how energy and mass relate. It controls the flow of time. It defines what is possible. If tomorrow something were discovered to travel faster than light, not just in theory, but in testable, repeatable observation, it would overturn modern physics, not just tweak it, not just revise it. It would collapse it. The theories we use to describe the universe, general relativity, quantum electrodynamics, the standard model, all assume that c is an upper bound. Remove that, causality itself begins to fall apart. Some speculative theories, like two kinds, propose particles that always move faster than light, but they have never been observed, and their inclusion leads to paradoxes, time loops, energy violations, non-local communication, and so they remain in the realm of thought experiments. Real particles, real forces, real observations, all obey the light speed limit, even gravitational waves. The ripples in space-time detected in 2015 from colliding black holes travel at the speed of light. Even neutrinos, nearly massless, barely interacting particles, do not surpass it. Even cosmic rays, the fastest particles known, obey the boundary. It is, in the end, a rule written into the quiet grammar of the cosmos, not an arbitrary law, not a technical detail, but a principle, a structure, a boundary with purpose. It lets the universe evolve without contradiction. It ensures order from chaos. K provides the slow, steady background against which all things happen. The speed of light is the rhythm of reality. The question that remains in this gentle drift through light and its constraints is why the speed of light has the value that it does. Why not faster or slower? Why 299,792,458 meters per second? Why this number and not another? The truth is, in nature, it's the number itself. The digits are a result of our measurement systems, meters, seconds, our human units. What truly matters is not the number, but the role it plays. And in the quiet equations of physics, the speed of light is more than just a speed. It becomes the conversion factor between space and time. This is why, in some natural units used by physicists, it's called Planck units, the speed of light is set to 1 dot, not as an approximation, but as a choice of scale, because space and time are fundamentally linked, not separate entities, but two views of a deeper geometry. Spaktesha. To understand this, imagine space and time as threads woven into a single fabric. Light does not move through this fabric. It defines its angle. When something moves at the speed of light, it doesn't age. It doesn't experience time. Photons, the particles of light, do not tick. From the moment a photon is emitted, say, from a star, 10 billion light years away, to the moment it reaches your eye, for the photon itself, no time has passed. This is not poetry. Time stops entirely for anything that moves at the speed of light. And yet, in our world, only massless particles like photons can attain this state. Anything with mass must move slower. Why? Because as an object approaches the speed of light, its relativistic mass increases. This is not to say it becomes physically heavier, but rather it resists acceleration more and more. It takes more and more energy to speed it up, and at light speed, that energy becomes infinite. This is why a spaceship, no matter how powerful, can never accelerate a human to light speed. The energy required would be infinite. The engines would break. The fabric of space would resist, so we are confined, bound, slipping just below the speed of light. Always chasing, never catching. This is not a punishment, but a structure. It preserves causality, because if information could travel faster than light, effects could precede causes. A message could arrive before it was sent. A particle could appear before it was created. Physics, which rests on consistency, would unravel in the equations of special relativity. Events in space-time are separated into three categories: time-like, space-like, and light-like. If two events are time-like separated, one can affect the other. If they're space-like, they cannot, not even in principle. No signal, no influence, no effect can travel faster than light. This division is absolute, so the speed of light is not merely fast. It is defined-itional. It is the boundary between what can be connected and what cannot. It defines the edge of, now, the limit of knowability. Now, think about how this principle touches every corner of the cosmos. When a star goes supernova 5,000 light years away, we see it 5,000 years later. We are not seeing the explosion as it is, but as it was, the past, written in light. Every telescope is a kind of time machine. Every observation is an act of watching ancient photons finally arrive. Galaxies, comets, quasars, their current state remains hidden until light brings us the update. So even the act of seeing is an act delayed. You are never looking at what is. You are only ever looking at what was, and light, at its unchanging pace, is the courier of the universe. Now consider how this relates to the fabric of space itself. In modern physics, space is not empty. It has structure. It can stretch. It can ripple. Gravitational waves, detected by LIGO, travel at the speed of light. These are not waves in matter, but in space itself, ripples in space-time generated by the most violent events, black hole mergers, neutron-star collisions, and yet they obey the same speed limit, even when space itself trembles. The ripple moves at c. In quantum mechanics, too, respects this boundary, though particles in quantum entanglement seem to influence each other instantly across great distances. No usable information travels faster than light. This has been tested repeatedly with photons, electrons, even ions. No violation has ever been found. So entanglement, strange as it seems, does not allow for faster than light communication. It only reveals the interconnectedness of probabilities, not cause, not signal. Now, take this understanding deeper into the vacuum. You may imagine a vacuum as empty, but it is not. Quantum field theory tells us the vacuum is alive with fluctuations. Particles and antiparticles appear and annihilate. Virtual particles dance for a fleeting moment, and even here, light obeys its speed. Photons in a vacuum still move at c, unaffected by these flickers. Only in media glass, water, diamond, does light slow, because it is absorbed and re-emitted, scattered, bent, but in a true vacuum, it races unhindered. This is why the speed of light in a vacuum is considered the true limit. It's not just fast, but maximal. It is the benchmark against which all other velocities are measured. And yet, there are still questions in some extensions of known physics. Speculative models like loop quantum gravity or certain versions of string theory. The idea emerges that the speed of light might vary under extreme conditions, perhaps near the Planck scale, perhaps in the first instance after the Big Bang, perhaps in certain warped geometries of space, but to date, no observation confirms this. Every test, every beam, every particle reaffirms the limit. Even the most energetic cosmic rays, particles, moving with nearly unimaginable speed, still fall just short, a few nanometers per second slower. Never see, now reflect for a moment on how this limit shapes even your daily life. GPS satellites orbiting Earth must account for relativity, because their clocks run differently. The signals they send beams of light and radio must adjust for time dilation. If not corrected, GPS would fail within hours. Your phone's location, accurate 2 meters, depends on this cosmic speed limit. Lasers in laboratories used to cool atoms, measure vibrations, or track movement, relying on the consistency of unmocking light behavior. Fiber optic cables, pulsing with light, carry vast oceans of information. The internet itself, the stream through which you hear, see, and learn, is bounded by this pace. Light is not a luxury, just the bloodstream of technology and the limit. It is not an obstacle. It is what makes the system stable. The entire framework of science, from Newton to Einstein to today, rests on this foundation. Change the speed of light, and everything else begins to tilt. So we do not mourn the limit. We embrace it, because it keeps the universe ordered, predictable, understandable. It gives time a direction. It gives space a scale, and it gives us a way to see, to know, to remember, because every photon that reaches us, every glow that drifts across the void, is a whisper from the past, a message that light, steady and silent, has carried across the cold not faster, not slower, but exactly as it must, as it must. In this softly unfolding understanding of light, we begin to see how deeply the speed limit is etched, not just in equations, but in reality itself. It is not merely a cap placed upon the universe, it is the rhythm by which everything unfolds. Now, turn, quietly, to the world of fundamental constants, alongside the speed of light. There are other numbers that seem to be written into the very structure of nature: the gravitational constant, the Planck constant, the fine structure constant. All of these values, unchanging and inexplicable, describe the fabric of the universe with uncanny precision. Yet, of all these constants, the speed of light is the one we experience most directly. We see it when lightning flashes and thunder follows, delayed by the slower speed of sound. We observe it when the sun sets, knowing the light we see left the solar surface 8 minutes ago. We rely on it when we glance into mirrors, unaware that light has traveled to the surface and back in billionths of a second. We are surrounded by light, and its fixed pace underpins everything from vision to navigation to the very idea of distance. But how did we come to discover this speed? And how did we confirm it is not infinite? In the centuries before Einstein, the prevailing assumption was that light moved instantaneously. Ancient Greek philosophers debated whether sight was the result of something leaving the eye or something entering it later during the Renaissance. Galileo attempted to measure the speed of light by standing atop distant hills with lanterns. He observed the delay between uncovering a lantern and seeing the response. The conclusion, frustratingly, was that light was too fast to measure by such means. The first true evidence came not from Earth, but from Jupiter in 1676. Danish astronomer Ole Rachmer noticed that the eclipses of Jupiter's moon Io occurred at slightly different times depending on Earth's position in its orbit. When Earth was moving away from Jupiter, the eclipses appeared late. When approaching, they appeared early. Rachmer realized this was due to the time it took light to reach us. It was not instantaneous. It had a finite speed. His estimate was crude off by a large margin, but the principle was sound. Later, more accurate measurements by Fizeau and Foucault, using rotating mirrors and light beams bounced through air and water, refined the value. Eventually, with the development of electromagnetic theory by James Clerk Maxwell, it was discovered that light was an electromagnetic wave, and its speed could be predicted from other measurable constants. And then, Einstein's theory of special relativity completed the puzzle. Light was not just fast, it was the same speed for all observers, regardless of their motion. This was astonishing. If you run toward a beam of light, it does not appear to come faster. If you flee from it, it does not slow. It is unchanging, mutable. From this, Einstein derived a new understanding of space and time, one in which they were not absolute, but relative to the observer. Time dilates, length contracts, stadia dissolves, all because light remains loyal to its pace. And yet, its constant speed raises subtle mysteries. Why should something be the same speed for all observers, even those moving rapidly toward or away from the source? It's not how we expect the world to work. If you throw a ball while running, its speed is your speed, plus the ball's. But with light, terrace, no addition. If you shine a flashlight while running at nearly the speed of light, the beam still leaves you at sea, and someone watching you will also see it moving away at sea. This defies everyday intuition, but it has been confirmed in experiment after experiment. Time slows down for moving observers. Distances contract in their direction of motion. Mass increases with speed, all to preserve this universal truth. Light speed cannot be exceeded or diminished. Now, consider something curious. Light is not the only thing that travels at sea. Gravitational waves, as mentioned earlier, also propagate at this speed. and the forces that bind matter like the electromagnetic field also operate at c. This suggests that the speed of light is not about light in the narrow sense, but about information. It is the ultimate speed at which cause can lead to effect. The universe has built-in protection against violations of causality. It prevents paradoxes, backward time travel, and inconsistencies. And the enforcer of this rule is C. So what happens if you try to break the limit? Not theoretically, but in practice. Particle accelerators, like the Large Hadron Collider, hurl protons to over 99.999991% the speed of light. Their mass increases by orders of magnitude. Their energy becomes tremendous, yet the speed never quite reaches c. The accelerator's magnets must account for relativity in every cycle. The detectors, too, must predict where and when particles will arrive, accounting for the distortions in time and space that occur at near-light speeds. Even photons, which naturally move at c, cannot exceed it. They are bound to it. There are no observations, which light moves faster than this speed in a vacuum. This gives rise to a poetic truth. The universe enforces discipline. There is order beneath the chaos, symmetry that cannot be shaken. Now, shift your attention from physics to perception. Light shapes how we see, but it also defines how fast we can know. If something happens on the moon, we see it a little over a second later. If something happens on Mars, it takes minutes. The nearest star system is over 4 years. The Andromeda Galaxy, more than 2 million years. The cosmos is not just vast in space, is vast in time, and light draws. The map, the speed of light, defines the cosmic horizon, the furthest point we can see, bounded by the age of the universe. Beyond that horizon, light has not yet had time to reach us, so we do not know what lies there. Not because of clouds, not because of obstruction, but because of the limit. And in the early universe, when everything was compressed and hot, photons could not travel freely. The cosmic microwave background. Earliest light we can see was released about 380,000 years after the Big Bang. Before that, the universe was opaque, so our vision is not infinite. It is capped by time, by distance, by light. And yet, through careful observation, we reconstruct the past. We map the expansion of the universe. We measure the redshift of galaxies. We detect the subtle stretching of space-time, all through light. Its constancy becomes a ruler, a clock, a guide. Even when photons are absorbed, scattered, or delayed, the principles remain. And so, from the quantum scale to the intergalactic, from the birth of the universe to the microsecond pulses of GPS satellites, the speed of light governs all. It is the fastest speed, key, but it is also the firmest boundary, a horizon of meaning. No ship outruns it, no idea outpaces it, no theory survives without it. It is written into Maxwell's equations, defines the cones of causality in space-time diagrams. It fixes the shape of the equations that describe black holes, inflation, and cosmic rays. And still, it is gentle. You do not feel its limits, but they are there. Behind every image, every glimmer, every signal. They hold the cosmos in balance. They draw the line between what is possible, and what is not. Not because the universe is cruel, but because it is precise and light in its quiet journey across the void, whispers the rules to us. It moves not with fury, but with finality. At 299,792,458 meters per second, no more, no less. Always, always. The constancy of light speed is so foundational, so woven into the very equations of nature, that scientists use it to define the very units of measurement we rely on. Since 1983, the meter itself has been defined as the distance light travels in a vacuum in 1/299,792,458 seconds. This makes the speed of light not something we measure in meters per second, but rather something that defines what a meter is. In that quiet redefinition, something profound happened. Light stopped being a traveler across space and became the ruler of it. To measure distance is to measure time. To measure time is to follow light. Clocks, especially those of exquisite precision like atomic clocks, depend on counting electromagnetic waves. Cesium atoms vibrate in predictable rhythms, so predictable that the second is now defined by counting 9,192,631,770 of these oscillations. And those oscillations are light too. Not visible light, but microwave radiation, just a slower cousin on the electromagnetic spectrum. So, in a way, our entire concept of time is light ticking. And in GPS satellites, those floating timekeepers, in Earth's orbit, both time and light come together in practical choreography. Each satellite constantly broadcasts its time signal down to receivers on the ground. The device notes how long the signal took to arrive, knowing the speed of light. It calculates the distance to each satellite. With signals from 4 satellites, it triangulates position in 3 dimensions, plus time, but without accounting for relativity, without understanding that time ticks slower in orbit due to motion and faster due to gravity. Your location would be off by kilometers within minutes. This is not theoretical. It's happening now. It's every time someone checks a map, orders a taxi, or calls for help. The speed of light governs the precision of modern life, and still, light resists being touched. It is both wave and particle, and neither in the classical sense. It carries energy, it has momentum, yet it has no rest mass. You cannot ever catch a photon and slow it down to zero without destroying it in the process. A photon is born traveling at sea and will continue at sea until it interacts absorbed, reflected, scattered. This curious nature gives rise to strange outcomes. From a photon's own frame of reference, if such a thing could exist, no time passes. The instant it is emitted, it is also absorbed. The journey from star to eye, from explosion to telescope, from atom to all these are experiences that take time for us, but none for the photon itself. It simply is on a trajectory, obeying only the rules written into the structure of space-time, and those rules become warped when gravity bends space. Einstein's general theory of relativity revealed that mass doesn't just pull, it curves the geometry of space and time. Light, though massless, must follow these curves, so near massive bodies, like stars or galaxies or black holes, light bends, not because it feels a force, but because the shortest path, the geodesicus, no longer straight. This bending of light is not imagined. It has been observed in 1919 during a solar eclipse. Arthur Eddington measured starlight being deflected as it passed near the sun. The result matched Einstein's predictions and made headlines around the world. Light curved. The speed limit remained untouched, but the road had bent beneath it. Later, with the advent of powerful telescopes and radio observatories, scientists observed gravitational lenses' entire galaxies warping space to bend the light of objects behind them, sometimes forming rings, arcs, or duplicate images. In this way, the speed of light becomes both a rule and a revealer. By measuring how much light is delayed or distorted, astronomers can map invisible things, dark matter, black holes, even the expansion of the universe itself. Light does not lie, but it may be delayed. It may take millions or billions of years for its message to reach us, and by the time it does, the source may be gone, extinguished, transformed. We see galaxies not as they are, but as they were. We watch stars dying that have already faded. We glimpse collisions that occurred before our species emerged. We read light like an ancient letter delivered slowly by a cosmic courier. And yet, though always traveling at sea, light can still be slowed. Not in the vacuum, but through matter. When light passes through water or glass or air, it interacts with atoms. It is absorbed and re-emitted, not destroyed, but delayed. This gives rise to refractive indices, how much a medium slows light in air. The speed is about 99.97% of c. In water, about 75%. In glass, it can drop to around 66%, depending on composition. But the photon itself, in each individual flight, still moves at c. It is the interruptions, the pauses between emissions, that add up to delay. And this slowing enables lenses, prisms, and rainbows. It allows microscopes, telescopes, eyeglasses. It enables focus of image, focus of thought. Even in fiber optics, where pulses of laser light carry internet signals across oceans, the delay is due to refractive slowdown. We are talking to each other at nearly the speed of light, yet that nearly matters. And even as we transmit beams through vacuum, we remain chained to that unyielding constant. This has consequences for computation. As chips become smaller and faster, nodes traveling inside must respect the time. It takes 4 lighter electrons to move from one place to another. At the bleeding edge of speed, even a millimeter of wiring becomes a delay. Timing is everything, and in space exploration, latency becomes a burden. To send a command to Mars takes over 10 minutes. To receive a reply takes another 10. No real-time conversation. No joystick control. Rovers must be autonomous. Probes must be patient. Humans must wait. And that waiting becomes profound when you think about interstellar travel. If we could build ships that approach the speed of light, which is still far beyond our current capabilities, the travelers inside would experience time more slowly. This is time dilation. To them, the trip would be short. To those left behind, decades may pass, or centuries. And returning home might mean returning to a world unrecognizable. This idea of going out and coming back triggers paradoxes, but the math holds. The speed limit remains. You can approach c, you can get infinitesimally close, but not reach it, not pass it. If you could, equations would yield imaginary numbers. Causality would be broken. Events might precede causes. The arrow of time would dissolve. So nature draws a boundary, and it is this boundary that defines light, not just as an experience, but as a guardian. It guards the order of events. It guards the framework of physics. It guards the difference between the possible and the absurd. All this encoded in a number 299,792,458 meters per second, an arbitrary number in human terms, perhaps absolute in physical ones. And yet, it is not the fastest we can think. The human brain, in pondering light, transcends its speed, not by moving faster, but by imagining. In a moment of thought, you can picture yourself at the edge of a black hole, watching light struggle to escape. You can visualize a quasar 1 billion light years away. You can simulate the journey of a photon from a distant star, cross eons into the lens of a telescope. In this way, thought is not faster than light, but it is freer because it is not made of mass or particles, or waves. It is made of understanding, and understanding is timeless. So while we cannot send ships faster than c, can ask questions faster than c, we can explore implications, we can contemplate limits, and in doing so, we find a kind of peace, because in the quiet certainty of light speed, we find something stable, a benchmark, a law, a lullaby of physics. Whether you are awake or asleep, the light continues. The constants hold, and the universe whispers, only this fast, no faster, no slower. And so it is, though it is. The constancy of light speed does more than preserve the rules of causality. Causality, it underpins every known interaction in the standard model of particle physics. The exchange of photons, the very mechanism of electromagnetism, depends on the rules dictated by this universal speed. All charged particles interact through the electromagnetic field, and this field propagates changes not instantaneously, but at the speed of light. When an electron moves, its field changes, but that change does not reach other charges immediately. Instead, a ripple begins to spread a disturbance in the electromagnetic field, traveling outward at light speed. And it is this ripple of photon that carries the force, not a packet, like a courier, but a quantum excitation of the field itself. This is how light connects things, slowly, surely, and never faster than the rules allow. Even in the subatomic realm, where particles flicker in and out of virtual states and energy seems momentarily borrowed from nothing, these processes still respect the ultimate speed limit. Nothing, no information. No influence moves faster than light in a vacuum. The equations allow no shortcuts. Even theoretical particles, like tachyons, hypothetical entities that will move faster than light led to mathematical contradictions. They would require imaginary mass, violate causality, and suggest that the future could influence the past. No such particle has ever been observed, nor is one needed to explain the workings of the universe. Reality is better behaved than our speculations. There are no loopholes, no backdoors in the code of the cosmos, just the slow, measured unfolding of interactions. With light as the messenger, this constancy helps define what's called a light concept from space-time diagrams in relativity. Imagine a flash of light at a point in space and time. The light spreads out spherically, forming a cone in the fabric of space-time. Everything inside that cone is causally connected, able to influence or be influenced by the original event. Everything outside the cone lies in the elsewhere, not past, not future, but forever unreachable. This geometric boundary is set by C, and it is through this lens that we understand not only motion, but existence itself. For any event in the universe, the speed of light defines what can happen next. Galaxies separated by more than 13.8 billion light years, suing to the expansion of space, may never see each other's light. They drift apart, not because they are moving through space faster than light, but because the space between them is stretching. Light, still moving at its same steady pace, finds the goalposts forever retreating. This is how the observable universe is shaped, not by the contents of space, but by the speed of its illumination. Even when light is bent or delayed or redshifted into invisible wavelengths, it still arrives as the only witness to ancient events. Redshift caused by the expansion of the universe stretches the light waves as they travel. The farther a galaxy, the more stretched its light. This is not due to slowing down. Speed remains c, but the wavelength grows longer and the frequency grows lower. The energy of each photon diminishes, yet its velocity does not. We learn from this stretching. We map it. We extract timelines. We estimate ages. Light, as always, is the language. And yet, even with this foundation in theory, there are still frontiers where the rules seem blurred. In the quantum world, things are not always intuitive. Experiments like the famous double slit reveal that photons behave as both particles and waves, depending on how they are observed. In entanglement, two photons share a quantum state, such that measuring one instantaneously determines the state of the other, even across vast distances. But even here, no information travels faster than light. The entanglement is correlated, not causal. You cannot send a message or a signal using this phenomenon alone. The outcome is random. It respects the speed limit. This limitation is not a flaw. It is a feature. It keeps the universe orderly, even in its strangeness. And when researchers use lasers to cool atoms to near absolute zero, reducing their motion almost to a standstill, but photons that carry away heat still move at c. The speed does not change even as temperature drops. Even as matter becomes nearly still, light moves with certainty in a world full of uncertainty. This certainty allows measurement in interferometry. Two beams of light are sent along different paths, then recombined. Tiny differences in their phase reveal motion, deformation, or delay. This is how LIGO detects gravitational waves, ripples, in space-time from massive events like black hole mergers. The instrument measures displacements smaller than a proton, using light's unwavering speed to reveal cosmic tremors. Without that precision, the waves would remain silent, and in laboratories, researchers bounce lasers between mirrors to measure distances, times, and even changes in fundamental constants. Light is the ruler, the judge, the chronicle. In medicine, laser pulses map tissues. In manufacturing, they cut with impossible accuracy. In art, they scan and preserve. In communication, they encode billions of messages. Yet light itself remains unchanged. It moves at 299,792,458 meters per second in a vacuum always. And everywhere it can be delayed, redirected, absorbed, but never outrun. And though humans have come close accelerating particles to 99.9999999% of C in giant colliders, like the Large Hadron Collider, the final sliver of speed remains elusive. No matter how much energy is added, a particle with mass will never reach C. The energy required becomes infinite. The mass increases. Time dilates. Length contracts. But the barrier holds. This barrier defines more than motion. It defines cause and effect. A universe without a speed limit would be chaotic. Messages could arrive before they were sent. Particles could violate conservation laws. Thermodynamics would unravel instead. We find structure. We find a cosmic traffic law that governs not just photons, but the unfolding of history. A law that makes the universe readable in the deep quiet of this law. There is something comforting. A rhythm. We live in a cosmos where starlight from the past continues to arrive, where signals bounce from satellites in orbits, where fiber optic pulses encode your voice, your thoughts, your songs, and through it all, it remains not a maximum, but a guide, a silent whisper in the vacuum. Asterisk. It's the breath of the universe's structure, the keeper of the timeline, a quiet constant that defines what it means to move. Light, ever steady, ever precise, not only serves as the boundary of speed, also defines how we perceive time itself in the realm of special relativity. The passage of time is not absolute. Instead, time is intimately tied to motion. As an object approaches the speed of light, time slows down for it relative to a stationary observer. This isn't a philosophical idea or a curious trick of measurement. It is a measurable, repeatedly confirmed truth of physics. The faster something moves, the slower its internal clock ticks. This is time dilation. Astronauts on the International Space Station experience it ever so slightly because they orbit Earth at about 28,000 kilometers per hour. Their clocks tick just a little bit slower than those on the surface. When they return, they have aged imperceptibly less than their earthbound counterparts. It is not noticeable, but it is real at the extreme end of motion approaching the speed of light. This effect becomes dramatic. A hypothetical spacecraft traveling at 99.9999% the speed of light would experience time so slowly that what seems like a year on board could correspond to thousands of years on Earth. And yet, no matter how fast that craft goes, it'll never reach the speed of light. This isn't a matter of engineering. It's woven into the mathematics of space-time itself. If you take the equations of motion from Einstein's theory and plug in values that approach the speed of light, the denominator of the equation, the part that accounts for mass, and energy approaches zero. That drives the energy required toward infinity. And infinity is not just a big number. It's a boundary that nature itself refuses to cross. For massless particles like photons, this boundary is different. They are born at the speed of light, and they remain there. They don't accelerate or decelerate. They exist in motion, and here lies a strange implication. From a photon's perspective, if it could have one, there is no time at all, because time dilates infinitely at the speed of light. A photon experiences no passage of time between emission and absorption. Whether it travels 1 centimeter or 10 billion light years, the journey in its own frame is instantaneous. That is difficult to conceptualize because human brains are anchored in a world of slower speeds. But in physics, such concepts are consistent in TESTABL. In this sense, light becomes a bridge between events and space-time, a connection without delay in its own terms, yet one that takes time in hours. It is through these principles that we understand more than just motion. We begin to understand reality itself. When astronomers peer into the deep sky, they are not merely looking into distance, they are looking into time. The light from distant galaxies has taken millions, even billions of years to arrive. The farther we look, the older the light. And so, with each photon captured by a telescope, we catch a glimpse of what the universe used to be. Some of the light we now observe began its journey long before Earth existed. It was already en route while the Milky Way was forming. Past uncounted stars, dodged clouds of gas, skimmed the edge of black holes. It may have been bent by gravitational lensing, its path distorted by the curvature of space-time around massive objects. It may have been stretched by the expanding universe, its wavelength lengthened into the infrared or even microwave bands. Yet its speed never changed. It remained steady, constant, reliable, the foundation of cosmic archaeology. And when we listen to the cosmic microwave background, the faint afterglow of the Big Bang, we are not hearing echoes. We are receiving light, light that has been traveling for over 13 billion years, slowed only by its interactions with matter in the early universe, and finally released when atoms first formed. That light, too, arrives at the same speed. Everything else may change temperature, density, structure, but C does not. And this universal speed limit governs more than light. It defines the causal structure of the universe. It tells us what can influence what. Imagine star collapsing into a supernova. The blast sends shock waves through space and light through the void. But the news of that explosion does not reach Earth immediately. We must wait. The photons must travel. Even if the star is destroyed, its final light will still arrive on time. And so it is with all events. We can never observe something before its light has reached us. We can never react to something before we've seen or felt its influence. This is what keeps the universe ordered, predictable, understandable. The speed of light is not just fast, it's defining. It tells us what is real and when, even in the invisible spaces between galaxies, where photons may travel for eons without interaction. The structure they follow is shaped by this rule, and the rule applies not only to light, but to all interactions that require a signal. Gravitational waves, recently detected for the first time, also travel at the speed of light. They ripple through the fabric of space-time, announcing colossal collisions between neutron stars or black holes. They carry information, strike light, and they respect the same limit. This is not coincidence, it's coherence, because in Einstein's theory of general relativity, the structure of space-time is described by geometry. That geometry governs how things move, how forces act, okay, and how signals propagate. And at the heart of that geometry is C, every known law of physics, from the simplest Newtonian mechanics to the deepest quantum field theories constructed. With this speed as a boundary condition, It is not an obstacle. It is the stage, and yet, for all its foundational importance, the speed of light is often misunderstood. It is not fast in any absolute sense. It is simply the rate at which space-time permits causal influence, and in practical terms, it is often limiting. It means that even with our fastest computers, our quickest messages, and our most powerful observations, we are always looking into the past. We never see anything in real time, not even ourselves. The light from your own hand takes time to reach your eyes. It means we cannot coordinate perfectly over long distances. It means that deep space missions, like those to Mars or beyond, require delayed commands. It means that if life exists around distant stars, we will never hold a real-time conversation. And it means that travel between stars, ever possible, will always require patience. Science fiction often imagines faster than light travel, warp drives, wormholes, tachyon fields. These are creative constructs, not yet matched by reality, because all experimental evidence, all theoretical models, and all observed behavior support the idea that light speed is absolute. That does not mean we will never discover something new. But if we do, it will need to preserve causality. It will need to reconcile with the constancy of c. It will need to explain why, so far, nothing has contradicted this ancient limit. And in the meantime, light continues. It bounces, reflects, refracts. It glows and flickers. It encodes data, heats, surfaces, nourishes plants, reveals the shapes of atoms and the structure of DNA. It defines time, defines distance, defines speed, and in its silence, it teaches us a lesson of restraint, of boundaries, of the deep logic behind the flickering stars and the slow drift of galaxies. In the end, the speed of light is not a restriction, it's a rhythm. The universe pulses at this speed. It speaks in its language, and we listen, quietly, as one peers deeper into the structure of physical law. The constant speed of light continues to appear, not as a quirk of electromagnetic radiation, but as a central pillar of all known reality. It threads its presence not only through relativity, but also through quantum field theory, thermodynamics, and even the equations governing particle physics. The speed of light is the ratio between the units we use to define space and the units we use to define time. In fact, in the International System of Units, the meter is currently defined by how far light travels in a vacuum in 1/299th, 792,458 of a second. This means that c is not only a physical limit, but also a definitional, constantive fixed relationship between our understanding of space and time. To say that light has a speed limit is, in a deeper sense, to say that nature itself has boundaries. These are not barriers built by choice. They are woven into the very architecture of spectrumit in theoretical physics. Its attempts to unify general relativity with quantum mechanics often encounter this boundary again and again. Whether one is examining string theory, loop, quantum gravity, or the behavior of quantum entanglement, the speed of light remains a regulator. Even when particles appear to influence one another instantly, such as in entangled states, the actual transfer of usable information does not break the light speed barrier. Correlations are revealed, but no message is sent faster than c. This is not accidental. It is a reflection of causality itself, of the idea that causes must precede effects, and that information must have a finite channel through which it moves. Any physical law that would allow faster than light communication would also allow violations of causality scenarios where the effect appears before the cause, or where paradoxes begin to surface. The so-called grandfather paradox is one such illustration where faster than light travel might permit a person to influence the past in ways that undo their own existence. To protect the logical consistency of the universe, nature prevents. The barrier is not just technical, it is philosophical. It defines the boundary between what is observable and what is unknowable. and light steady, neutral, and ever present is the agent of this definition. It is through light that we see, measure, and understand, from the flicker of distant quasars to the structured ripple of gravitational lensing. It is light that maps the cosmos for us, even when invisible, as in the case of gamma rays or X-rays or infrared pulses. The information it carries defines the edges of our understanding. In practical terms, this boundary of speed manifests in many of the technologies that now define daily life. Fiber optic communication, for instance, sends pulses of light through hair-thin glass fibers across cities and continents. These pulses, encoded with data, obey the same constraints as cosmic photons, atoned of kilometers per second. They are still finite. Signal latency, though minimal, still matters. Global communications, server pings, internet protocols respect the speed of light. Even when milliseconds separate the sending and receiving ends in financial markets, where speed translates to advantage, trading firms build direct fiber lines or even use microwave towers to reduce latency by fractions of a second. These systems are not constrained by processing power or decision-making. They are bound by physics. The only way to shorten delay is to shorten distance. In this world of ultra-fast signals and real-time data, it is a humbling realization that light itself still sets the pace in astronomy. This limit is both a gift and a constraint. When we observe a supernova in a distant galaxy, we are not witnessing an event as it is. We are seeing it as it was. The light may have traveled 10 million years to reach us. That galaxy, in its current state, is unknowable until its light from today arrives eons from now. We live within a light Kona domain, defined by the time it takes light to reach us. Everything beyond that is history still in transit. And so, the observable universe is not a boundary of the cosmos itself. It is a boundary of time, sphere, not of matter, but of delay. This also means that any knowledge of the universe is necessarily delayed. We cannot interact with the present beyond Earth, not even with the moon. All space missions operate with delay. Messages to Mars take minutes. Messages to the outer planets take hours. Voyager 1, humanity's most distant probe, now takes more than 22 hours to send a signal back to Earth. And yet, every single one of those messages obeys the same silent, constant pace. And so, our window into the cosmos is framed not just by what we can detect, but when we can detect it. In theoretical cosmology, the constancy of light speed is also embedded into the very structure of the universe's expansion. When Edwin Hubble observed that distant galaxies are moving away from us and that their light is redshifted, he was not witnessing galaxies in flight through space. He was witnessing the stretching of space-time itself. As the fabric of the universe expands, the light that travels through it stretches too. This redshift is not a result of motion in the classical sense. It is a result of geometry. The longer the light has traveled, the more stretched it becomes. This is why the most ancient light, the cosmic microwave background, is now in the microwave spectrum. It's once high-energy radiation. It has been diluted over billions of years of expansion. And yet, throughout all this change, speed never altered, because the expansion of the universe does not drag photons. It stretches the space between the wave fronts of light. The wavelength increases, the frequency drops, but the speed remains c in black hole physics. Light's behavior takes on yet another fascinating dimension. Near the event horizon of a black hole, the gravitational field is so intense that light itself struggles to escape. At the exact radius of the event horizon, the escape velocity equals the speed of light. This means no photon, no signal, no particle can leave, not because light slows down. It does not. But because space itself is curved inward so steeply that all paths lead inward. from the perspective of a distant observer. Any object falling into a black hole appears to slow down, its light red shifting infinitely as it approaches the event horizon. It never seems to quite vanish. It fades, it elongates, it freezes at the brink. But from the perspective of the infalling object, time continues. It crosses the threshold. It experiences something we cannot witness because its light can no longer reach us. And so, once again, the speed of light defines not only motion, but visibility. It defines what can be known and what must remain hidden. This has implications in information theory as well. The notion that no information can travel faster than light protects systems from chaos. It means that events in one part of the universe cannot influence another without delay. It builds a lattice of influence, a causality map that links every moment to a neighborhood of potential, and this, in turn, defines the order of events. If faster than light communication were possible, could send messages to the past, opening doors to paradoxes, but would see as a limit. Sequences remain intact. Cause precedes effect. Messages travel forward only. The structure of the cosmos remains coherent, and so the speed of light is not simply about light. It is about information. It is about influence. It is about the fabric of what is possible. And even though we may imagine technologies or civilizations that could bend this limit, no experiment has ever contradicted it. Particle accelerators, like the Large Hadron Collider, push protons to over 99.999999% of light speed. At that velocity, time slows for them. Mass increases. Energy requirements skyrocket. But the barrier remains unbroken, no matter how much power is applied. The particles approach, but never reach C. The same applies to neutrinos, to electrons, even in extreme conditions, in quasars, in neutron stars. In the early universe, the limit holds dot, and so light continues to move at the same steady pace, defining the edge of every possible motion, every equation in electrodynamics. In general relativity, in quantum electrodynamics, contains C, not because light needs it, but because reality does. It is a symmetry of balance, a rule, and in that rule, we find structure, predictability, stillness within the motion. In the quantum world, the speed of light serves as a boundary between realms of probability and certainty. When quantum field theory attempts to describe how particles interact, the mathematics is bound by locality, the idea that particles interact at the same point in spacetime. And the limit to how far and how quickly one interaction can influence another is once again governed by C-virtual particles. Short-lived fluctuations that blink in and out of existence must still obey the restrictions of this speed limit. Even the briefest ripple in the quantum vacuum cannot transmit a signal or causally influence another region without respecting the light barrier. The probabilistic rules of quantum mechanics are strange, but they are not chaotic. Their constraints emerge from the very structure of spacetime. This concept leads naturally to the idea of the light cone, a diagram used in relativity to define what events can influence one another. Every point in space and time has a future light cone and a past light cone. Anything that lies outside of these cones cannot be causally connected to the point in question. If an event lies within your future light cone, it means light coned, travel from you to that event. If it lies in your past light cone, it means light from that event could have reached you. But anything outside those cones is causally disconnected. Even if something significant is happening there, no signal, no information can reach you faster than C. Thus, the light cone becomes more than a diagram. It becomes a boundary of knowledge, and a border between what can happen and what can be known. These limitations are also foundational to the famous no-signaling theorem in quantum mechanics, even though entangled particles exhibit correlations that defy classical intuition. They cannot be used to transmit information instantaneously. No measurement choice made on one particle can influence the outcome of a measurement on its partner in a way that breaks the light speed constraint. Quantum entanglement is eerie, but not lawless. It respects the speed of light, not by slowing down, but by refusing to carry messages. In all our understanding of physics, C stands firm. From the vast arc of general relativity to the granular texture of quantum fields, K, it is ever present. Even when physicists imagine alternate models of the universe, simulations, multiverses, hidden dimensions, the presence of a finite communication speed remains, because without it, structure dissolves, chaos reigns, predictions fail. This finite limit also has thermodynamic implications. The causal horizon, the maximum distance over which changes can influence a system, plays a role in how entropy, temperature, and energy flow behave in relativistic systems. The speed of light defines how fast disorder can spread, how quickly heat can equilibrate, and how sharply boundaries between order and randomness can evolve in the early universe. During the brief moment after the Big Bang, this became critical. The inflationary epoch, a period of exponential expansion, occurred so quickly that regions of the universe moved out of causal contact with one another. Yet, they remained strangely uniform in temperature and structure. This paradox, the horizon problem, led to theories that posit a faster-than-light expansion of space itself, not of matter within it. This was not a violation of the speed limit, because nothing traveled through space faster than c. Instead, space itself grew, pulling points apart at speeds exceeding the ability of light to traverse them. Once inflation ended, the universe resumed its expansion at subliminal rates, and light began to knit the cosmos back together. The speed of light also acts as a boundary for what we can explore, even in theory. In cosmology, there is the notion of the particle horizon, the maximum distance from which particles could have traveled to us since the beginning of the universe. It defines the edge of our observable universe, about 46 billion light years. In radius, beyond this limit lies not necessarily nothing, but simply that which we cannot see, that which has not had time to reveal itself, that which remains, for now, inaccessible. It's humbling to realize that this barrier is not due to a lack of effort or technology. It is not something that can be overcome with better telescopes or faster ships. It is a hard edge, drawn not by tools, but by time and engineering too. The finite speed of light plays a role in many seemingly mundane designs, in satellite communications. Every bit of data sent between Earth and a geosynchronous satellite experiences a round-trip delay of over half a second. This lag affects phone calls, video streams, and real-time controls. In deep space exploration, the delays become even more profound. Commands sent to Mars rovers take minutes to arrive. Operators on Earth must anticipate outcomes and send sequences of instructions that the machines will carry out without its feedback for several cycles. The Voyager probes, drifting through interstellar space, now take nearly a full day for signals to arrive. Their faint transmissions, encoded in ancient formats, whisper back at the edge of our reach. And always, that whisper obeys C. The farther we go, the longer we wait. And so, we must imagine futures where distance will always mean delay, not just of travel, but of thought. Even within Earth, this boundary manifests in high-frequency trading, in GPS synchronization, in atomic clocks. Timing must account for the tiny delays introduced by the speed of light. A few nanoseconds matter. Precise systems must know where the satellites are and how long the signal took to arrive. In order to correct for that delay and produce accurate positions, GPS, in fact, is one of the most precise systems humans have ever built, and it is deeply dependent on Einstein's theory of relativity. The clocks aboard satellites tick slightly faster than those on Earth's surface because they are in a weaker gravitational field. They also tick slower because they are moving rapidly in orbit. A combination of these effects must be corrected, and those corrections are measured in the context of c. Without them, GPS would drift by kilometers each day. So the speed of light, once thought to be the domain of distant stars, now governs even the act of finding your location on Earth. In research settings, particle physics continues to test the limits. The discovery of the Higgs boson, the analysis of neutrino oscillations, the search for dark matter, all are constrained by the same universal constant. Even gravitational waves, ripples in the fabric of space-time itself, move at the speed of light. When two black holes collide, the resulting gravitational signal fans outward at c, arriving at detectors like LIGO and Virgo as gentle distortions in laser beams. These detectors must account for the light delay across their arms. Even a fraction of a wavelength matters. When LIGO first detected such a wave in 2015, it confirmed that not only does gravity ripple, it ripples in lockstep with light. Different force, same speed. This constancy reveals something more profound: the unification of forces in space. Light is an electromagnetic wave. Gravity is a curvature of space-time, but both are governed by the same maximum velocity. It suggests that beneath the diversity of nature's forces, there is a deeper symmetry, a blueprint in which distance, time, and causality converge. And so, when we speak of c, we are not merely speaking of light's journey. We are speaking of the fabric that hosts all journeys. It is not a speed in a traditional sense. It is a conversion factor between space and time. It is a ratio that turns seconds into meters, that allows equations to relate one dimension to another. It is the slope of the universe. And while light happens to travel at this speed, it is not because of some special permission. It is because light, having no mass, travels the only way it can at the speed permitted by space-time for any massless particle. If there were no light, the number c would still define the geometry of the cosmos. If all photons vanished, space-time would still have a structure, and c would still be its scale. It is this deep presence that gives c its power, not just a speed, not just a barrier, but a framework, a principle, a rule that holds firm, even as the rest of nature dances around it. And, in this quiet precision, the universe whispers its consistency. To better understand why there is a speed limit at all, it helps to go back, not to Einstein, but further, to the geometry of space itself. In classical Newtonian mechanics, space and time are treated as separate entities. Events happen in space, and they unfold in time, but one does not influence the structure of the other. You could imagine an absolute invisible grid of space stretched infinitely in every direction, and a ticking universal clock counting the passage of time. But this view changed fundamentally with Einstein's special relativity in 1905. He showed that space and time are not separate. They are parts of a unified structure, space-time, and within this structure, different observers might disagree about distances or durations, depending on how fast they are moving relative to one another. But all observers, no matter how fast they're going, will always measure the speed of light in a vacuum to be the same. Approximately, it's 299,792,458 meters per second. This constancy seems counterintuitive. One might expect that if you were moving toward a beam of light, it would appear to approach faster, or if you moved away from it, it might seem slower. But that is not the case. Instead, what changes is your experience of time and distance. Your clock ticks differently. Your ruler shrinks. This was one of the revolutionary consequences of special relativity, that the laws of physics remain the same for all inertial observers. And the speed of light is a universal constant, not just the speed of photons, but a fundamental property of spacetime, geometry itself. This idea leads to two key effects: time dilation and length contraction. As an object approaches the speed of light, time appears to slow down for it relative to an outside observer. is not an illusion. It's a real, measurable effect. Particles traveling at near light speeds inside particle accelerators decay more slowly than they would at rest. Their internal clocks genuinely tick more slowly from the perspective of a stationary observer. Likewise, lengths contract in the direction of motion. A spaceship flying past Earth at close to the speed of light would appear shortened to an observer on the ground. Again, this isn't a trick of the eye. It is a built-in consequence of how space-time warps in response to relative motion. These distortions become more and more pronounced as you approach the speed of light, but they also mean that no object with mass can ever reach that speed. To accelerate a mass to the speed of light, you would need to supply it with infinite energy. That's not a metaphor. The equations of special relativity literally contain a term in the denominator that approaches zero as you approach light speed, causing the energy requirement to blow up toward infinity. This is why photons, which are massless, can travel at sea, but anything with mass must always move slower, and so the universe quietly draws a boundary. This barrier isn't just practical, it's structural. It protects the integrity of causality, it prevents contradictions, it keeps the order of cause and effect intact. This brings us to another implication of light speed, the impossibility of faster-than-light communication. Many thought experiments in science fiction imagine sending signals, ships, or even people faster than light. But even in speculative ideas like warp drives or wormholes, the fundamental constraint remains: information cannot be transmitted in a way that would allow observers to disagree on the order of events. This is because, in relativity, the order of two events A and B can depend on the observer's frame of reference. If the events are separated by distance that light could not traverse in the time between them, in such cases, one observer might see A happen before B, while another sees B before a dot. This seems strange, but is entirely allowed, so long as A and B cannot causally influence each other. But if you could send a signal faster than light, you could send a message into your own past. You could create paradoxes. You could receive a message before it was sent. Physics cannot allow this. It is not merely convenient, it is inconsistent. To preserve causality, the universe uses the speed of light as a ceiling. Every law, every interaction, every ripple in any field must obey this limit, not because of some mechanical enforcement, but because the very equations describing space-time and energy require it. The constancy of C also implies a deep symmetry in physics known as Lorentz invariance. This symmetry tells us that the laws of nature look the same to all observers moving at constant speeds, regardless of their direction or velocity, provided they're not accelerating. This invariance is fundamental to all modern physical theories, from electromagnetism to quantum field theory. If the speed of light were not constant or not a limit, this symmetry would break down. Many of the equations that describe reality would cease to function properly. Predictions would fail. Even in string theory, loop, quantum gravity, and other candidate theories of everything, this limit persists, woven into the core of the mathematics. It is not a suggestion, it is a requirement. When physicists test for deviations in the speed of light, searching for tiny hints of new physics, or violations of Lorentz invariance, they consistently find none. The universe, it seems, is remarkably committed to its own boundaries. But where does this speed come from? Why not something else? Why 299,792,458 meters per second? It turns out this number is not arbitrary, but also not unique. It is only fixed when we define our units. In fact, the meter itself is now defined based on the speed of light. Since 1983, T, the International System of Units, defines the meter as the distance light travels in a vacuum in 1/299,792,458 of a second. So by definition, the speed of light in a vacuum is exactly that number. But more fundamentally, speed emerges from the properties of electric and magnetic fields. James Clerk Maxwell, in the 19th century, derived a set of equations that unified electricity and magnetism. From these equations, it became clear that light is an electromagnetic wave, a disturbance in the electric and magnetic fields, traveling through space, and the speed of that wave depends on two constants: the electric permittivity of free space epsilon ebb and the magnetic permeability of free space mu ebb. The relationship is simple. C equals 1 square root epsilon eb mu ebb. These two constants describe how electric and magnetic fields interact with space. They define how charges attract or repel and how currents generate magnetic fields. So, in a deep sense, the speed of light is not about light. It is about the medium. It is about how empty space, the vacuum, responds to electromagnetic forces. And this brings us to the idea that space itself has properties. Even in the absence of matter, even in a perfect vacuum, space is not truly empty. It has structure, it has rules, defines how fields behave, and that structure determines the fastest speed at which changes can propagate. This is why physicists often say, light doesn't define c defines light. Photons travel at c because they are massless and because the vacuum permits disturbances in the electromagnetic field to move at that speed. If the vacuum had different properties, if epsilon eb or mu eb were different, the speed of light would be different too. But the structure of physics would still enforce a maximum. This also explains why light travels slower in materials like water or glass. When photons enter a medium, they interact with atoms, being absorbed and re-emitted or scattered, and this effectively slows their progress. But in a pure vacuum, where these interactions do not occur, light travels at c, the fastest possible speed. Nothing with mass can reach it. Nothing with information can exceed it. It is the edge, a possibility. It defines the shape of the universe, the bounds of the observable, and the rhythm of cause and effect. And it is always constant. In the quiet vastness of space-time, the speed limit is more than a boundary. It is a governing principle, an unspoken agreement that defines how the universe communicates with itself. As we drift deeper into the meaning of this boundary, we arrive at the very structure of space-time diagrams, those neat little charts used by physicists to map out events and their relationships in time and space. These diagrams often show what's called a light cone, and within this cone lies a truth as still and absolute as any river's flow. The future is limited by the speed of light. Imagine standing at a point in event in time and space. From this event, a cone of possibility opens forward into the future and backward into the past. The sloping edges of that cone represent paths that light could take. Nothing outside the cone can affect you now. Nothing you do now can affect the regions beyond that cone. These are the limits of causality. Within the light cone, all physical interactions must occur. Every beam of sunlight, every wave from a distant radio tower, every burst of gamma rays from a collapsing star, none of them can violate this framework. Because if they did, if something were to arrive faster than light, it would no longer be confined to the cause and effect structure of our universe. It would be a temporal orphanage signal with no past, an effect with no clear cause. This is more than philosophy. It is the very basis of relativistic field theories, such as quantum electrodynamics, the theory that describes how light and matter interact. These frameworks are built on the assumption that information and energy do not propagate faster than c. If that assumption fails, the entire edifice begins to collapse. In fact, within quantum theory, the same speed limit still holds. At first glance, this may seem confusing. Quantum particles can appear to exhibit strange, non-local behaviors, like entanglement, where two particles affect each other instantly across vast distances. But even this does not allow faster-than-light communication. When two entangled particles are measured, okay, the results are correlated in a way that defies classical expectations, okay? But the outcome of any individual measurement is random. Information travels from one particle to the other faster than light. So, while the correlations are spooky, as Einstein once put it, they do not violate causality. Even in the quantum world, speed of light is the gatekeeper. This is deeply connected to the structure of quantum field theory, where particles are seen as excitations in underlying fields. Each field, be it the electromagnetic field, the Higgs field, the gravitational field, has its own light speed limit. These fields ripple, but no ripple travels faster than light in the vacuum. The speed limit is baked into the mathematics itself, and yet, despite its foundational role, light, there are still whispering tiny questions that physicists ask about this limit. Could there be particles we haven't yet discovered that move faster than light? These hypothetical entities are known as tachyons. If they exist, would always move faster than light. They would have imaginary mass and peculiar behaviors. But no evidence has ever been found for them, and most physicists believe they are likely forbidden by deeper principles. If they did exist, they would bring with them a cascade of problems, violations of causality, breakdowns of energy conservation, and inconsistencies in well-tested theories. So far, no particle accelerator, cosmic ray detector, or astronomical observation has seen a hint of such particles. Instead, what we see is remarkable consistency. No matter how high the energy, no matter how extreme the conditions light speed holds, even the gravitational waves detected by LIGO ripple outward from cataclysmic events like black hole mergers, travel at the speed of light. This is not a coincidence. In Einstein's general theory of relativity, gravity is a curvature in space-time itself, and the changes in that curvature, those ripples, move at c dot. In fact, the 2017 detection of gravitational waves from a neutron star collision confirmed this even more precisely. Just 1.7 seconds after the gravitational wave passed Earth, gamma rays from the same event arrived, over 130 million light years of travel. The two signals stayed nearly in lockstep, demonstrating that gravitational waves and light waves move at the same cosmic speed. This observation also helped rule out many exotic theories that predicted variations in the speed of gravity. Once again, nature showed its preference for simplicity. And yet, speed limit is not always obvious in our daily lives. We don't experience delays when we turn on a flashlight. The photons reach the walls in less than a blink. We speak to someone across the room and the sound, though much slower than light, seems instantaneous. But zoom out to a planetary scale or beyond, and the delay becomes real. It takes light just over 1 second to travel from Earth to the moon. It takes about 8 minutes to arrive from the sun. The signals we send to Mars rovers can take up to 22 minutes one way, depending on the distance between the planets. Even within our solar system, light begins to stretch time into space and beyond. It takes over 4 years for light to reach the nearest star system, Alpha Centauri. It takes tens of thousands of years to traverse the Milky Way, and to see a galaxy 1 billion light years away is to look 1 billion years into the past. We are never looking at the universe as it is, only as it was. The finite speed of light turns the cosmos into a kind of natural time machine photon, a messenger from a distant moment, traveling across unimaginable gulfs of vacuum. It's not that these distances are so vast we can't imagine them. It's that the speed of light gives those distances meaning in time. The delay is not incidentally essential. It is a feature of the universe's architecture. So when we ask, why does light have a speed limit? We are really asking, why does space have the structure that it does? Why does causality have edges? Why can't information leap across the void without resistance? The universe does not seem to offer answers to these questions in the form of opinions or preferences. It offers equations, constants, constraints, and see this quiet, elegant number sits at the heart of them all. It unifies energy and mass. E equals mx squared. It unifies space and time into one four-dimensional fabric. It draws the line between the possible and the impossible. And in doing so, it allows a universe to exist where rules can be trusted, where effects follow causes, where the stars shine, not all at once, but in the slow unfolding of light across billions of years. It is humbling to know that no matter how fast we go, no matter how clever our machines become, this limit will remain. We can approach it, we can curve around it, but we cannot pass through. And so the universe drifts, slowly, surely, under the silent governance of this limit. Everything that has ever happened, every signal, every heartbeat, every flicker of thought, has obeyed it. The speed of light is not just a number. It is a promise that the fabric of space and time will not tear. It's a promise that information cannot outpace itself. A promise that even in a universe of boundless wonder, there are still boundaries. And in those boundaries, we find not limitation, but structure, order, peace. There is a particular stillness in the knowledge that all things, whether near or far, grand or small, must obey the same immutable law. This constancy is not loud or visible. It does not demand applause, but it is always there beneath the surface of every physical process. It guides the motion of galaxies, just as it shapes the flicker of a candle. This final section turns gently toward the deeper layers of this truth, the mathematical skeleton that holds the universe together. To understand why light has a speed limit, it helps to look again at the structure of space-time, not just as Einstein described it, but through the lens of deeper theoretical frameworks, those that attempt to unify everything into one coherent explanation. At the heart of this search lies a branch of mathematics known as Lorentz invariance. This concept is central to both special and general relativity. It states that the laws of physics remain unchanged under transformations that include shifts in space and time, provided those shifts obey the speed of light as a ceiling, in simple terms, no matter where or when you are, and no matter how fast you are moving, as long as it's below c, the laws of physics will look the same to you. This isn't a mere curiosity. It's a fundamental rule written into the equations of motion for particles, waves, and fields. It is the reason that the Maxwell equations, which govern how electric and magnetic fields behave, naturally give rise to a fixed propagation speed, one that matches the speed of light in vacuum, long before Einstein formulated relativity. James Clerk Maxwell had already noticed this. His equations predicted that electromagnetic waves light itself should travel at a fixed speed. That speed was not derived from experiment. It was baked into the math. And when measured, it turned out to be the same constant that all later theories would inherit, approximately 299,792 kilometers per second. This value is not a limit in the sense of a mechanical cap. It is not a barrier imposed from outside. Rather, it is the very framework that space-time uses to differentiate between what is and what can be. In some theories, such as string theory and loop quantum gravity, physicists attempt to explore what space-time is made of at the smallest scales. These theories suggest that space and time might not be continuous, but rather composed of tiny, discrete elements like pixels on a screen or threads in a tapestry. Even in these speculative ideas, the speed of light persists. It is preserved not just as a rule for particles, but as a defining quality of the geometric and topological structure of the universe. It is the speed at which disturbances in the field of existence propagate. It is the hum through which reality vibrates. Consider for a moment vacuum polarization. In quantum electrodynamics, the vacuum is not empty. It teems with virtual particles that briefly blinked in and out of existence. These quantum fluctuations affect how light moves through space. In fact, they slightly alter the observed values of physical constants. Yet, even with this underlying sea of activity, the speed of light remains the highest attainable speed. Virtual particles do not cheat the system. They play within its rules. In dense media, such as glass or water, light slows down, but this is not a violation of the limit. It is a result of the photon being absorbed and re-emitted, delayed by interactions with atoms. The true speed limit c in vacuum remains untouched. Some researchers have explored whether the speed of light might have been different in the early universe. These are called varying speed of light theories. They propose that in the moments after the Big Bang, light may have traveled faster than it does today. This could, in theory, solve certain puzzles about the uniformity of the cosmos. But these ideas remain speculative. The evidence so far continues to support a constancy across space and time. In the domain of cosmology, the implications of a speed limit ripple outward. For instance, there are regions of the universe that lie beyond our cosmological horizon, far for light from them to have ever reached us since the birth of the cosmos. These regions exist, but they are forever out of contact. We can never see them, not because of distance alone, but because light, bound by its own maximum speed, has not had enough time to reach us. This limit defines the observable universe, a bubble around us about 93 billion light years in diameter. Anything beyond that may exist, but it is hidden behind the curtain of causality. The speed of light draws the edge of our vision, and this brings us to, perhaps, the most quietly poetic idea of all. The night sky is a memory. When we look up, we are not seeing stars as they are. We are seeing them as they were. Light from the Andromeda galaxy took over 2 million years to reach us. Light from the farthest quasars began its journey when the Earth was still forming. The photons that strike your retina tonight began moving long before humans existed. Without a speed limit, there would be no such delay. The sky would be a mirror of the present, not a museum of the past. But with sea as the gatekeeper, the night becomes a layered archive of time itself. Each glimmer is a time stamp. Each flicker is a fossil of light. In astrophysics, this is more than poetry. This is the basis of look-back time, the technique by which we study cosmic history. By observing galaxies at increasing distances, we reconstruct the universe's past. And so, the speed limit of light does not only impose a boundary, it enables a method. It slows time enough for us to witness it, to study it, to understand it. Even in technology, the speed of light is central. Fiber optic cables, satellites, laser communication all depend on light as a carrier of information. The delay in these systems, though minimal, must be accounted for. Global positioning systems, GPS, correct for the time it takes light signals to travel from satellites to Earth's surface. They also correct for time dilation caused by gravity and velocity effects, predicted by Einstein and confirmed with exquisite precision. Without factoring in the speed of light, GPS would drift by kilometers each day. Your phone would not know where you are. Planes would veer off course. Precision farming, military coordination, and autonomous systems would all fail. The constant sea is more than a curiosity. It is a pillar of modern civilization, and, in deeper philosophical terms, it is a symbol of restraint, one that reminds us of the finitude of our reach. We cannot know the entire universe at once. We cannot signal across it instantaneously. We cannot leap from star to star like skipping stones on a pond. We must wait. We must move slowly. But in that slowness, there is structure. In that structure, there is clarity. And in that clarity, there is peace. Just as gravity binds matter together, the speed of light binds information to time. It keeps causes ahead of effects. It prevents paradoxes and makes science possible. And so the universe continues quiet, ordered, expanding under the rule of this unseen constant. It is not a wall, but a rhythm, not a jail, but a song, a cosmic tempo to which all particles dance. And in the silence of space, in the gaps between stars, this limit hums softly, steadily, always the same, asterisk, good night, dot, dot, dot.